I didn't tell you this, but what's V?
IR.
It'd be I over, or I times R, right? So 0.3 times 15 is going to be a little less than 5. 4.8, 4.7. Oh, give or take about 4.5. What's that?
Exactly 4.5.
4.5. Now, I guess I should have known that. I didn't think so. Now, when I put a second R across here, if I put it here, what's going to happen to I1? Current's going to drop. But the current doesn't drop. It goes from 0.3, the total current. The current here goes from 0.3 to 0.45 amperes. This doesn't change, which means there has to be a second outlet, or a second path for charge to flow. Because there's no way for the same power supply, 4.5 volts, you're going to drive more than 0.3 amperes through this resistor, this bulb, with this power supply. Ain't going to happen. Only way you can get that extra current is to open up a second path. So now we have an I1 and we have an I2. The only thing I can say for certain is whatever this total current is, which is what's going in and what's coming out, it's got to be split up between what goes this way and what goes this way. So here's what I know. I know that the total or the net resistance is going to be equal to whatever my voltage is divided by my total current, which is 0.45 amperes. So I have 4.5 divided by 0.45, so now I've got 10 ohms of total effective resistance. It was 15 when it was just 1. Now adding a second one doesn't increase it, actually decreases it. Current goes up, resistance goes down. So what does R2, what is R2 then? It's going to be 1 over R, original R. Actually, it's going to be R equivalent, R net, minus 1 over R1. Is going to be equal to 30 ohms. You see where the logic comes in for that? The total current output is higher. Same voltage. You'll never get more than this voltage anywhere in this circuit if this is the only power supply. Probably should have drawn that out there first. I wasn't trying to make it tricky. Fancy. The net result is now you have a 30 ampere or a 30 ohm resistor here, because you've got 15, 0.15, 0.3 amperes, respectively for each of these branches. So what's the power draw across all? Here's what I know. I know the work required to drive 1 coulomb across. It's going to be equal to, well, not even a coulomb. It's going to be equal to Q times V. So the rate of power, dW dt, rate of work required to push charge across here, it's going to be equal to, for a constant voltage, V dq dt, or V times I2. And it's just related to work. Now, given what I know, though, I can write V as I2 times R2. So to minimize how my calculations go into this, it's probably easier you write it this way and say that if I square the current and multiply it by 30, that'll be how much power draw occurs across that second resistor, or joules per second of power output. That's a light bulb. So, that number is 0.15 squared. 0.0225 times 30, so 0.06, 0.6 watts, give or take. 5.6, 0.7 watts. Oh, I left out my square. I did indeed.
0.675.
Watts. I sort of threw that in there at the last moment. What's that?
Those are not very powerful bulbs.
No, they're little tiny little bulbs. They're what you'd use for a Christmas tree or something like that. Okay. I'll leave it at that because I know we're running long.